Hey, check this out. It's a mock-up of the Gamebadge3 that I'm designing for the Midwest Gaming Classic 2023 workshop. The last two MGCs, we had a workshop where we assembled the original game badge. Has a little microcontroller, LiPo, and OLED screen. But now this one's in color, and it has a Raspberry Pi Pico, the most Optanium Cortex M0 you can possibly find. So ahead of the workshop, I want to make some videos where I show you how to actually program this thing, even though I'm still developing it. It's designed to have NES-style graphics using a tile background with sprites. The tile background is kind of the same as, well, pretty much the same as the NES. Sprites are obviously much larger. Sprites are only limited by draw time per frame. So yeah, let's talk about how to create the graphics. So these first few videos aren't going to be about assembling it because obviously I haven't gotten the prototype PCBs in yet. They're going to be about basically how the graphics are done. Let's get started. The last couple workshops I did with the Game Badge, everything was programmed in Microchip Studio, which is the development environment for Atmel devices. It's nice to develop in Microchip Studio since it's Visual Studio. However, you need a debugger or a programming device, in this case a UPDI programmer, Universal Programmable Debugger Interface. With the Pico, I was like, well, why don't we use Arduino? Arduino is not as pleasurable to code in. That's an understatement. However, it's pretty easy to get started with. Like in this case, we just get the Raspberry Pi boards for the manager. I'm not going to talk about that in this video, just a brief overview. So you set up the Raspberry Pi W. I was actually able to find quite a few of those off DigiKey, $6 each. And then I also created two custom libraries, Arduino libraries. Okay, so this is where you put your libraries. So I created two libraries, Pico ST7789, which is a DMA-based ST7789 LCD driver based off the mbed ARM version. And I also created one that's a work in progress, Gamebadge Pico library. Right, so you'll need these two libraries installed as well as a few Adafruit libraries. But one thing that's cool about this is I'm actually using the Adafruit mass storage device. So the Raspberry Pi it's got a 2 megabyte flash on it. It uses 1 megabyte for the sketch and 1 megabyte for storage. So combined with some code that you can get off of the example files, it acts as a USB flash device on your computer. So the graphics I'm going to show you about here, you can actually create them on your computer, then just drag and drop them into this flash drive. And then you can load them using the file system in Arduino. I'm also using both cores. The Pico is a dual core processor. It's actually pretty easy to set up. Oh, here we go. Yeah. So when you start a stage or whatever, there's the palette, which is the total number of colors available to the system. And again, we're going to make this Nintendo-like, so it's 64 roughly. Load palette, this is the palette that you're using for the current screen. And then finally load pattern. Pattern is actually the bit defines of what all the characters look like. And on the original Nintendo, like let's say the original Nintendo had two buses. You had the code bus or the CPU bus, and then you had the PPU bus, the picture processing unit. It would have I would just call it a GPU or VDP. It would have its own memory basically. And at the start, it had an 8K. So like all of the graphics for like Super Mario Brothers fit inside an 8K ROM. And then the code, which was on the CPU side, was a 32K ROM. So 40K total for that game. I think there's a recent homebrew called MicroMages. These people decided to make a no mapper 8K plus 32K game for the Nintendo. And if you look that up on YouTube, there's some excellent explanations on how the memory works. Found this program called YY-CHR. And it's some software that was made by somebody in Japan. What's their name? Let's find out. YY-CHR. No, that's probably why it's called YY. There you go. Let's zoom in it. That's their wiki. Yeah, so you can use this to create, well, old school graphics. And the thing that's cool about it is it forces you to create them in the correct way. Let's talk about that now. That older game badge I showed you earlier, the game that I programmed for it, I called Moon Force. well, this is the total tile set. Well, I've got this grid in the background so you can see how everything lays together. Now this was for that monochrome OLED, so everything is just black and white here. But I'm going to use this as a basis for actually just showing you how this works. Okay, so if you look at the Nest stuff, so in memory, so see how you've got 16 by 16 characters here? So you got 16 this way and 16 down. So there were two different pattern tables. There was there's one for the background graphics, which I think was called the name table. And then there's one for sprites. So in this case, if you scroll down one page, you see they've got a sprite layer here, which has the cat. So if you had this screen plus that screen in ROM, that was a total of 8K. And that was the most that your PPU could access. So what later games would do, they would either use a RAM to update the data dynamically. Think like Mega Man 1 or Contra. Or they would have a fancy bank switcher like the MMC3, which would swap out certain portions of these tiles based off commands from the CPU. So that's more like an MMC3. So something like, like the Teenage Mutant Ninja Turtles arcade game. So they would animate the characters just by doing huge bank swaps. But as far as the Nintendo is concerned, it's still looking at the same 8K of memory. Anyway, back to this. So let's, all right, let's go back here. This thing is kind of picky about what kind of bitmaps it'll open. It seems to either want monochromatic ones or indexed ones, but the indexed ones need to have all 256 indexes populated. Now let's just try it. I loaded a file just to try it. Nope, it did not like that. What about this anime woman? Let's paste over this waifu. Oh, it's this one. Sorry. Oh, did I forget to index that? Oh, yeah, it's RGB 8 bits per color. Okay, go to index color. So index color, like if it's an 8-bit index color image, every pixel has a 1 byte value assigned to it. And that byte refers to an index. Oh, there you go, index color. It refers to an index in a list of colors. So it's kind of like old school, like how VGA graphics worked. All right, it's something kind of weird. Like it adds these. Look at these little hairs that it adds here. It's like a caterpillar or something, like one of those fuzzy caterpillars. What do those things turn into anyway? Do they turn into moths? I don't know. I'm not a caterpillarologist. Yeah, I just said that. I don't care. So if we look at the color table, so again, you see this is 16 by 16, so it's 256 colors. And in this case, it's chosen, well, I used the Windows palette. So it just found the closest possible thing. But if we import this, well, I guess we'll see what color it is. All right, so now let's, wait, well, it's certainly not a PSD now. It's going to be a bitmap. See, they changed this too. It's like, oh, if you do Control Save As, it saves a copy, or it's like they're just trying to waste our time. There we go, 8-bit. So it's 8 bits per pixel versus 24 bits per pixel. There we go. Nice. All right, I'm going to go Control C. I'm going to go back over here and whoop, there we go. Nice. Let's get this graphics out onto a tray or something. All right, so look down here in the lower right-hand corner. So this portion here that I'm putting my mouse over, these are the palettes. So see, when I move my mouse, you see how they're in groups of 4. So Nintendo is an 8-bit system, but the graphics are actually 2 bits. 2 bits per pixel, which means 4 colors. Typically, it was black and then 3 other colors. Well, there's some limitations. Like, so the second set here, the second set of 4, this is for the sprites. However, color 0 for each one of the sprites is the transparency. Plus, on this layer here, which is the tile colors, color 0 is the background. So you don't have to do it here, but on the real Nintendo, you would set one background color, and so all 4 of these would have the same color 0. You don't actually get 32 colors on screen. It's really 3 times 4, 12, plus 12 plus 1, 25 colors. All right, so let's do some other stuff here. I've already prepared some things here. So first of all, I'm going to change, down here before I do this. Now these are the possible colors. So this is the amazing Nest palette. Notice how like 1/5 of it is black. That's just the way the Nest palette is.
So I created a small C# program to generate my own palette file based off the superior Atari palette. Ah, look at all these colors. Rich Corinthian leather. I found some code that did hue, saturation, brightness, RGB, and then I just went through the steps of the hue color wheel. So anyway, what I did was I made a script that would generate that palette. So it just goes about 21 degrees for each column on the color wheel. Then it creates 4 brightness shades of each. So YY-CHR calls this a PAL file for a palette, but Photoshop calls it an ACT file for, I don't know what the heck it stands for. But check this out. So I can take that palette file I just loaded into this thing, and I'll go over here. Well, actually, it's already here, but I'll just redo it. So get rid of that. I will paste it. Oh wait, well, I guess we have 2 of them now. Great. So I'm going to take that. I'm going to rename it ACT. Now it's going to get the CLUT icon for color lookup table. Now if we go back over here, go to mode, color table, and I could say, oh, I want to load up. So the PAL file, all I did was change the extension, and then that should, yep. So see how our same palette's been brought over here into Photoshop. It's an ACT file, but all it is it's 256 3-byte groupings of RGB color. So it's 24-bit RGB then times 256. So it's, what would that be, 768 bytes? Yeah, but one thing I noticed is kind of weird is if you're over here and see how we don't have the whole palette now. If you save this with an incomplete palette, that other program, the YY-CHR program, doesn't want to load it. But I'm just showing you how you can make it compatible. All right, so this is the RGB PAL file down here, right? So over here, we go to palette table, which I've also created. So this is actually the palettes that you'll use. So on the Nintendo, a group of 4 tiles had to have the same palette color. A good way of thinking about that is like the blocks in Castlevania, how they were 2x2. And that was the minimum granularity for color. Now, we don't have that limitation with what I'm building. So if I click on one of these 16 palettes, see how it automatically changes the color of everything? Now, everything up here, Nintendo used bitplane graphics. So in memory, you'd have 2, because, well, the graphics are colored, but it also is high resolution, which is a big advantage it had over like the Atari or the Commodore 64. So you'd have 2 bits per pixel, but the way that was stored in memory was in bitplane. Okay. Well, okay, I'm trying to think of the best way to explain this. You know what? I'll just do a graphic like 8-bit guy would do. So a pixel can have 1 of 4 values. You can have 0, 0, 0, 1, 1, 0, 1, 1, right? And that gives you 4 possible choices. So in your palette here, I was like, okay, well, if it's 0, 0, it's going to be that color. If it's 1, it's going to be that color. If it's 2, it's going to be that color. If it's 3, it's going to be that color. So then what it does as far as how it's arranged in memory, so you got 2 bits per pixel basically, but the pixels aren't next to each other in memory, which would be called chunky pixel, which is like how the Master System or the Genesis works. They're separated by pages. That's called bitplane, which is how like the old IBM worked, Amiga, Atari ST, and also the Nintendo. So this software takes care of it for you automatically. And also I built it into the name table loader. So here's your first bit plane. It's a monochromatic dot pattern. And then if you go down 2K in memory, you have the next bit plane. Now obviously this is a cat. Let's say, well, I think we can just, so there's your first bit plane and there's your second bit plane. So let's say up here, this character, this color was meant to be bright, like 1, 1. So you'd have the first 1 here, and then in the bitplane copy of it down here, you'd have another 1. But let's say it's supposed to be a dark color. Let's say it's 0, 1. So in your first bitplane, you'd have a 0, and on your second bitplane, you'd have a 1. And those would be combined to create the 2-bit value. I think the reason that they did it that way back then was because it was easier to flip between 2 pages of data to get the second bit. It was easier to do that than it was to look at the next bit over, aka chunky pixel, which is like I said, what the Sega Master System or the Genesis does. The Sega Master System actually has a really high color density per cell. It's It's actually the same density as the Genesis. It's 4 bits per pixel, which is actually higher than some of the Super Nintendo modes. Well, that was a lot of boring explanation, wasn't it? But the thing is, you don't really have to think about that because I already converted that. So over here, all right, let's get to the fun part. So I'm going to say, okay, let's see. I got this blue here. I want to make it more of a teal. And then let's make this kind of a brighter blue. Well, we can always change that. So I can click on that. And let's say I want to go into, actually, let's color some of the text. So I'm going to give the bee some little decorations here. Oh, sorry. Happy little clouds. Oh yeah, the bee has a good friend here. Okay, you probably wouldn't actually shade it like that. Or you could do something like this. You could take the C. Yeah, see like this. This is so gaudy. This is something I would have done when I was like 10. I'd be like, ooh, that's cool. Oh, wait, we gotta, here, there you go. There you go. Gotta have your dither pattern. Wow, that's the coolest looking C. We're really just changing, a 2-bit value, but then depending on what you click down here, it'll apply the different palettes. And the way I have it designed in my program is that it uses the second bank of memory to hold the sprite data, although, you're really only limited by your RAM. So on the Nintendo, like I said, there was 2 banks per screen. So if it's 16 characters by 16 characters by 8 lines per character, that's 2048. And then times 2, because there's 2-bit planes, is 4096. There's your pattern data times 2 to get your sprite copy of that. There's 8192, which is the total size of the addressable space of the PPU. I've put in some nice shading for all the letters. We've got some color test bars down here. Now in our code, when we tell the system to draw a tile on the screen, we tell it what tile, and we also tell it what palette. Now, like for instance, like I mentioned, the original Nintendo, it was 2 bits for 4 cells. And the reason I did that was because, let's go into the weeds. It was 32 cells across by 30 cells high, which is 960. They had 1 kilobyte or 1024K of RAM to store each one of the screen backgrounds, and the default was 2048, which meant you could scroll between 2 screens. If you wanted to have 4-way scrolling, you needed to have 2 more K on the cartridge, which is one of the reasons why Nintendo cartridges were expensive, because a ton of them had extra RAM on them. Okay, so if you have a group of every 2 by 2, well, okay, let's say, so you got 32. Well, that's 16 by 15 if it's every 2 by 2. So that gives you a total of 240 different cell regions. Now, if it's 2 bits per pixel, well, the palette is 2 bits, which means you can cram 4 of them into a byte. So if you take this divided by 4, you get 60. Add that to 960, and there you go. Tile backgrounds plus the 2 bits per 2 by 2 cell memory takes up 1020 bytes, leaving extra 4 whopping bytes in that bank of memory. So that's why they did that. There are Nintendo mapper chips like the MMC5. I don't know how they do it, but they can actually add more attribute bits, which means they can have whatever palette they want on each cell instead of 2 by 2 cells. I think like Metal Slater Glory does that. Now in our system, we're not really limited by that. So each cell can have its own palette. So like, let's say you want the letter K to be orange. So when you draw that tile, you'd say, okay, I want palette 0 or 1, 2, 3. And if we wanted to cheat, we could also use the same patterns, the sprite palettes as well. But again, I want this to look fairly Nintendo-like. Also, if we start doing like 4 bits per pixel or even like 8 bits per pixel, it would greatly increase the size of RAM that we need. Because remember, we're loading this off of the flash and then putting it into RAM and then executing it. Let's say the graphics are all done. You're ready to put them over on the Pi. So here's our first screen. Then our second screen has this fish that was in the software, but then I drew this jellyfish here. I didn't shade his tentacles though. I guess I could if I wanted. Oh, and he could be all these different colors, right? So again, I'm just accessing memory how I want to. So I could grab sprite data from the tile data. It doesn't really matter. I'm just trying to make it NES-like just to help me understand it, and also so it's a better entry point for people, because A lot of people have, well, tons of people have developed Nest. They know how it works. They know more about it than I do. All right, so we're going to save as, and this is just going to be the pattern data, so the bits themselves. So we're going to call this Moonforce. Well, I don't think I'm going to reprogram Moonforce a third time, but just for an example. Okay, so now we need to export the palette data. So each one of, like, okay, let's say we go over here, I click that. See how, well, let me zoom in. See how it says 0, 0. So this color is an index of color 0, 0 on the palette. So the last one here would be what, 2F, 3F. So see how we change that. So this palette is just a reference to this palette number over here. This is the spectrum of RGB colors, and this is the palette as it refers to the tiles on the screen. Save RGB palette. And again, Nestari pal. Done. And then finally, save palette table, which again is the colors we're actually using on screen, not the total colors available. For some reason, I called this palette _0. Now you could dynamically change that as your game's running. That's how they would do like waterfall effects on the Nintendo and stuff. Then yeah, those 3 files that we just saved, you just put them onto the flash. I have it so that you press pause so the screen doesn't update while you're using the flash, because it can cause the screen to glitch. It doesn't cause it to crash, but it's just a little cleaner. Although 9 times out of 10, you won't be accessing this as a mass storage device, but you can. So these are the 3 things. So this is the dot pattern data. This is the RGB palette color, and this is the palette selection. Lovely Arduino code. You know, I did try the new Arduino IDE, and it's like, this isn't really any different. It's just gussied up. I'm sure there's so much crap. Why am I even speaking rhetorically? There's so much crap under the hood of Arduino that I'm sure they can't really change it without breaking everything. I like how that rumor that like IRS software still runs on COBOL emulated on modern computers. So I'm using both processors here, although I don't really want to get into that right now. But I'm going to use the second processor to actually blit the graphics and the first processor to do game logic. So before we can run, we have to load pattern, which are the dots. Then we load RGB, which are the colors, the available colors. Then we load the palette. And we have to load the RGB before we load the palette, because the palette's going to just create a reference link to the RGB values. The LCD is 16 bits per pixel. Basically what happens when you load the RGB, it does a bit packing conversion from 24-bit to 16-bit color, and then finds the closest approximation on the LCD. So load pattern. Yeah, so see how I have low bit, high bit? This is actually where it does the bit plane conversion. So it's going to open the file on the flash. Then I'm doing 512, so it's doing the one half of it is the tile pattern, the other half is sprites. Yeah, so we get the first one, we get the second one, and then we send both of them over to our library that I made, and it'll actually merge them into a 16-bit value, which will be used as the lookup table. And at first, I made a separate program to do the bit plane conversion, but this software does it fast enough. It takes like 1/10 of a second. You don't even know it. So you can have a loading screen, because remember, there's no loading on systems unless they have a CD-ROM. So load RGB. This is pretty simple. It opens up the file, and then it just says, okay, hey, 64 times in a row, load in 3 values, RGB, and then stick them into a memory buffer here. And then finally, load palette, same thing. It's going to load 32, because as you see, 16 by 2, loads 32 and updates the palette. So all that it really does is, so that's why, you have to do this first, because this populates the total number of possible colors. And then when you run update palette, what that does is like, okay, I'm supposed to be 0, 0. Okay, what's in color number 0, 0? And then it copies this 16-bit RGB value over into this position in the temporary palette memory. That way there's less math to do when you're blitting the screen. Oh yeah, you do have to set up a few things differently. Like I said, you have to do 2 megabytes, but 1 megabyte for sketch, 1 megabyte for file system. For whatever reason, the maximum SPI speed is 62.5 megahertz, which is actually almost exactly what the maximum SPI speed of the screen is. But in order to make that work, you have to run the Pi at 125 megahertz instead of 133 because it's going to do a divide by 2. And if you do 133 divided by 2, it won't work. You also have to use Adafruit Tiny USB as a stack, not Pico SDK. And then, of course, you select your port. Yeah, so this is all part of the mass storage device. You can get this from the examples. Then it creates a file system off of the mass storage device, which again is just the same flash you use to store your code. You do have to use another sketch, another Adafruit sketch in order to format your flash. I'll have links to that in the final project. Yeah, so when this sets up, setup 1 means it's happening on the second processor. Basically just draws a bunch of tiles on the screen. I don't want to get into this in this video, but this wind jump stuff, that's how you create like a static status bar. That's say that 5 times fast. The sheep's 6 static status bar.
So in this example, rows 0 through 12 are scrolling, and I got them scrolling in both directions. Plus we have the fish. And then rows 13 and 14 are static. So they're still using data from the pattern table in the background, but we're telling those rows not to scroll. You can also put them up there. And also, if you notice, there's also a window set for sprite draw, so you can make sure your sprites don't draw over your windows. Should be pretty comparable to what a nest does.
Oh yeah, so this screen is 240 by 240, but it's too hard to read text, so I made it 120 by 120. So it's like chunky pixels. So it's 15 by 15 characters wide and tall. So basically you can say, okay, on line 13 and 14, freeze the display and do not have it scroll. This repeating timer, this is actually the main game loop timer. So this thing is locked to 30 frames a second. I couldn't do 60, there's not enough time, and the limitation is the DMA speed. Core 1 loop. So right now it's just looking for a flag from the repeating timer if it should draw the frame. Then if it does, it draws the screen and then it does game logic. And then we have our pause function. So then down here, this is the core 2, or as I like to call it, core 1 loop. So if we get the flag to draw the frame, so see, we can use RAM flags to pass values between the processors. There's also a FIFO, but you don't really need to use it because they both have access to the same variables. So if we get the flag to draw the screen, then we say, okay, we're not doing that anymore. But if the system's paused, we don't do anything. And then I put some blips on the scope. Then send frame is where the magic happens. So basically it'll draw one character line, or character row, I should say. It'll draw one character row of the screen while it's DMAing the previous character row. So it gives it twice the throughput. And that's not even using dual core, that's just using DMA. Direct memory access. But, well, by a good amount of time, I mean, it takes like 1 millisecond to send that many pixels to the screen. So while it's doing that, I can render the next row of pixels, including the sprite blitter. And it takes about 70% of the DMA cycle time, so it works out good. And then it's double buffered, of course. Yeah, so it says, okay, we're drawing the frame. Send the frame is where it actually does all the DMA stuff. Then once that's done, it sets that to false. And the reason I'm setting those flags is so back over in the main loop, the game frame, it will sit there and wait for the frame to be finished drawing. Well, right here, it waits for the drawing to start. Then you could do any logic that doesn't require access to screen memory. I mean, you could access it, but you'd have screen tearing. Then it waits for the frame drawing to be false. And then just to be sure, it waits for the final DMA transfer to complete. Because remember, the screen drawing could finish, but the final DMA transfer would still be going on autonomously. And then this is where all your game logic would go. Well, there you have it. That's how you create graphics using YY-CHR for the Gamebadge3 coming to MGC this March, which means I have 3 months to program whatever game I'm going to make. I'm thinking maybe like a Venus-based game, because the screen is taller, so maybe it's like you're a spaceship flying through the atmosphere of Venus, and then, you could scroll down, and then you'd see like the rocks, and you would go up, and then you'd see like the upper atmosphere or something. Anyway, I'll make more videos about this as I proceed. I've just now got the graphics basics done, but I think this palette should work out pretty well. It does kind of suck that I kind of have to make everything work within the sketch right here, but it's not a big deal. You've got all this stuff here. Well, you also have these calls down here, like the stuff that actually services the callbacks for the mass storage device. Arduino's kind of messy, and it's been quite a long time since I've really used it, so I've kind of forgotten how a lot of it works. So if this works, that's good enough. But the nice thing is, people who do this workshop, they can just use their computer and they can install Arduino, install the drivers for the Pico W, and they're good to go. They don't need like a separate programmer or anything. And as an added bonus, since we're just soldering a Pico Pi W right onto my little circuit board that I'm going to make, I don't have to buy a USB port. Like the last time we did this, USB port was like the second most expensive item besides the screen. This one was to show you how to do the graphics. And so in the future, you can come back and reference all of these and make your own Gamebadge3 game. And it'll be the most amazing thing ever. All right, catch you next time.